The tires on your car right now are wearing out. Not eventually, right now, with every mile, every brake, every turn. What's coming off them is more chemically complex than most refinery products. 4 contact patches, each roughly the size of your palm, are the only thing between you and the road. Americans drive 3.2 trillion miles a year on those 8 square inches of contact per tire. But before rubber ever reaches your wheels, it travels through one of the most dangerous industrial pipelines on Earth. One that starts with a knife cut into a tree in Southeast Asia and ends with a substance OSHA has documented as a cancer risk for the workers who make it. Have you ever wondered how a tire actually gets made? Today we trace the entire journey, from plantation sap to the press that cures each tire at over 300 psi. Stay until the end, because what you're about to learn will change the way you think every time you pull out of a gas station. This is Directive 1. A tire looks simple, round, black, rubber. But a single passenger tire contains over 200 distinct raw ingredients: natural rubber, synthetic rubber, carbon black, sulfur, zinc oxide, silica, steel cord, fabric reinforcement, chemical accelerators, processing oils, all of it engineered to survive heat, load, impact, and speed at once. That complexity starts at the very beginning, roughly 7,000 miles from the nearest American highway. Thailand produces roughly a third of the world's natural rubber, by industry estimates. The process hasn't changed much since the 19th century. A worker makes a spiral cut into the bark of a rubber tree, Hevea brasiliensis, at a precise 30-degree angle, shallow enough not to damage the tree, deep enough to sever the latex vessels beneath. The white sap, called latex, drips slowly into a small cup mounted below the cut. Each tree yields roughly a cup of latex per day. A single tire needs roughly a pound of natural rubber. You can do the math on the scale required. The latex is collected before sunrise, when the sap flows fastest in the cool air. At the processing facility, it's mixed with formic acid to coagulate, to separate the rubber solids from the water. The result looks like pale, wet sheets of dough. Those sheets are pressed, dried, and smoked in long curing houses until they turn amber brown. Then they're baled and shipped to Japan, to Germany, to plants in South Carolina and Ohio. By the time natural rubber reaches a U.S. tire factory, it has crossed an ocean, changed form 3 times, and been graded for purity. But natural rubber alone cannot build a modern tire. It's too soft at high temperatures, too brittle and cold. Most of what goes into a passenger tire today is synthetic, and that's where petroleum enters. Synthetic rubber, primarily styrene butadiene rubber, or SBR, is cracked from oil refinery byproducts. The process starts with butadiene and styrene, both derived from naphtha, and polymerizes them in large reactor vessels into long polymer chains. Think of it like weaving millions of microscopic ropes out of crude oil molecules. The output is a pale, elastic solid that behaves similarly to natural rubber, but can be engineered for specific performance targets. Harder, softer, more heat-resistant, more fuel-efficient. A modern tire typically blends natural and synthetic rubber in proportions tuned to its specific application. Here's what most people don't expect about tire chemistry. It's not the rubber that defines performance. It's what you add to it. Carbon black is the ingredient most people have never heard of. It's the reason tires are black. Before the industry started adding it in the early 20th century, tires were white, the natural color of rubber. Carbon black does far more than change color. It is a reinforcing filler that increases tensile strength by several-fold and dramatically extends tread life. Without it, a tire would last a fraction as long. The problem is how it's made and what it does to the people who make it. Carbon black is produced by the incomplete combustion of heavy petroleum oils. The output is an ultrafine black powder, particles measured in nanometers, far smaller than the finest dust. By industry estimates, global production is on the order of 18 million metric tons per year. The International Agency for Research on Cancer classifies carbon black as a possible human carcinogen. Workers in carbon black mixing facilities, the Banbury mixer rooms where rubber compounds are blended, have long been a focus of occupational health concerns over respiratory exposure. OSHA has established permissible exposure limits, but enforcement varies, and in the early decades of the industry, workers operated without respirators in rooms that turned black within minutes. Put yourself in that mixing room. The temperature is running above 300 degrees Fahrenheit. The Banbury mixer, a machine the size of a small house with 2 counter-rotating rotors inside a sealed chamber, is kneading a batch of rubber compound with carbon black, silica, zinc oxide, sulfur, and processing oils. The friction alone generates intense heat. The batch is finished in roughly 4 minutes. Then the chamber opens and the mixed compound drops out as a steaming slab onto a mill below. That slab will be cooled, cut, and fed back into the process dozens of times before it becomes part of a tire. The compound exits the mixer like a dark, heavy dough. At this point, it is not yet rubber in the way we understand it. It is a thermoplastic blend, meaning it softens when heated and hardens when cooled. But it hasn't undergone the transformation that makes it a tire yet. That transformation has a name: vulcanization. Vulcanization was discovered by Charles Goodyear in 1839, essentially by accident. He dropped a sulfur rubber mixture on a hot stove and found it didn't melt. Instead, it cured into a stable, elastic solid. The sulfur formed cross links between the polymer chains, creating a 3-dimensional network that gave rubber its resilience. Every tire made today uses a version of that same chemistry. The rubber compound contains a precise amount of sulfur. The press provides the heat and pressure that triggers the reaction. Before vulcanization, the tire has to be built. The various rubber compounds, different formulas for the tread, the sidewall, the inner liner, are extruded into specific profiles and cut to exact dimensions. Steel belts, fabric cords, and bead wires are positioned with millimeter precision. The whole assembly is built up on a drum like wrapping layers around a cylinder, then shaped into a toroid, a donut form, by inflating the drum from inside. The result is called a green tire. It has the right shape, but it has no strength yet. The green tire goes into a vulcanization press. The mold closes around it with forces exceeding 300 psi of steam pressure. Inside, a bladder inflates to press the tire outward against the mold. Temperature reaches 320 degrees Fahrenheit or higher, sustained for roughly 12 to 15 minutes, depending on tire size. The sulfur cross-links form. The rubber transforms from a thermoplastic blend into a thermoset, a material that can no longer be remelted. The tread pattern is embossed into the surface. The tire opens from the mold as a finished structural component. Here's the take that will probably get pushback. The most dangerous part of a tire's life isn't the factory, it's after it leaves. Every time you brake, every time you corner, the contact patch between your tire and the road generates heat and friction. Rubber wears away. The particles released, called tire and road wear particles, or TRWP, are microscopic. By some estimates published in environmental science journals, U.S. vehicles shed on the order of 1 trillion grams of tire wear particles annually. Those particles don't disappear. They accumulate in road runoff, enter storm drains, and flow into waterways. A 2020 study published in Science identified a chemical called 6-ppd-quinone, a transformation product of an anti-ozonant added to tires to prevent cracking, as the cause of coho salmon die-offs in Pacific Northwest streams. The EPA has since classified 6-ppd-quinone as a substance of concern. The tire keeping you safe on the road is simultaneously shedding chemistry documented to be lethal to certain aquatic species. What's striking about this is the gap between what people see and what's actually happening. You see a black circle. The industry sees a 200-ingredient chemical system engineered to survive forces that would destroy most materials, and slowly converting itself to dust in the process. Every year, roughly 280 million tires are scrapped in the United States alone. Some are shredded for crumb rubber used in artificial turf or playground surfaces. Some are incinerated for fuel. A meaningful fraction end up in illegal dumps. The tire that started as white sap dripped from a tree in Thailand ends, billions of miles later, as particles too small to see, in the air, in the water, in the fish. The next time you pull out of a driveway, think about what's under you. A chemistry experiment that crossed an ocean, survived temperatures above 300 degrees, and is wearing itself away one molecule at a time to keep you moving. Every ordinary thing around you hides a process this violent and a supply chain this fragile. Almost nobody ever looks. Which everyday thing should we take apart next? Drop it in the comments and tell us where in the world you're watching from. Tittle. How is tire rubber made? The dangerous chemistry behind every mile you drive. Kani. End. Yas description. The rubber under your car started as tree sap in Thailand, and it travels through one of the most chemically violent processes in manufacturing to reach your wheels. By the end of this video, you'll understand what carbon black actually is, why vulcanization presses run at 300 psi, and what your tires are shedding onto every road you drive. A single passenger tire contains over 200 raw ingredients: natural rubber, synthetic petroleum polymers, sulfur, and a carcinogenic black powder. OSHA tracks closely. Tire manufacturing explained. From latex tapping in Southeast Asian plantations to Banbury mixer rooms running above 300 granarni, to the vulcanization press that cures each tire in minutes. This is the full industrial pipeline behind every set of tires on American roads. Plus, 280 million tires scrapped per year in the U.S., and the chemical found in tire wear particles that is documented to destroy salmon populations in Pacific Northwest streams. Brahmacha description. End. Your intro. Black chemistry. Hamanon. Intro. End. Your additional. Alt 1. How it's made. Danger. How is tire rubber made? The toxic process behind every set of tires. Alt 2. Number your scale. 200 ingredients, 300 psi, 280 million scrapped. The hidden world of tire manufacturing. ALT 3. What if? Crisis. What happens when the world runs out of natural rubber? ALT 4. With series tag. How tires are really made. The dangerous chemistry behind every mile. Directive 1. Additional end. Cover. A massive Banbury industrial mixer seen from below and to the side, its twin rotors caught mid-rotation through a thick, dark cloud of carbon black powder, the chamber glowing orange-red with heat at the edges. The black dust billows upward against a dark industrial ceiling. One shaft of industrial light cuts across the scene, illuminating the powder in the air. Deep black background, single bright orange-amber accent from the heat of the open mixer chamber. Korchakratini.